Waves. The powerful swells that pound coastlines worldwide are an ever-present, almost ignored wonder. Unstoppable and immense. Possibilities for use are endless. How can we transform the destructive power of ocean swells into a renewable energy resource? The answer is technology. Japanese scientists in the late 1970s developed a means of transforming the kinetic energy of waves into usable electricity, thereby beginning the use of wave power. Throughout the 1980s, 1990s, and 2000s, wave power technologies were redeveloped, rethought, and invented, revealing the bright possibilities of wave-generated electricity. The basic principle of wave energy is the transformation of the kinetic energy available from wave movement into electric power, a process that can be achieved through several systems. First and foremost among wave power facilities is the oscillating water column. The oscillating water column consists of a large concrete chamber, often built onshore, with a front cover that extends below the water line. As waves raise the water level within the chamber, air pressure increases. The compressed air is forced through a turbine located above the water line in the back of the chamber. The turbine turns, powering a generator located outside of the chamber. The air is pushed through the opening, which allows the pressure in the chamber to equalize. Air pressure within the chamber decreases when the water level lowers, allowing air outside the chamber to be pulled into the OWC, turning the turbine again. Depending on the plant, an OWC can produce between 0.5 kilowatts and over 250 kilowatts. The Pelamis mechanism is a newer technology in the realm of wave power. Pelamis is a floating, jointed pillar around 120 meters long with a diameter of 3.5 meters. It contains 3 sections, linked by joints which contain hydraulic pumps. The up and down motion of the waves moves the joints, which works the hydraulic pumps, which in turn increase the air pressure in a small chamber within the Pelamis. Compressed air is forced through a turbine into a low-pressure chamber, allowing the pressure to equalize and be reused. The turbine is connected to a generator, from which the electric energy is transferred through submerged power lines to a power plant on the mainland. Recently, the Archimedes wave swing mechanism has risen to popularity in the world of wave power, with a possible large development off the Oregon coast. The mechanism consists of 2 submerged cylinders anchored to the ocean floor. About 21 meters, or 69 feet tall, the Archimedes wave swing uses 1 cylinder attached to the seafloor and 1 buoyant cylinder to generate electricity. The outer cylinder rises and falls relative to the attached cylinder with the movement of the waves. The attached cylinder contains a magnetic bar, and the outer cylinder contains a spool of copper wire. The movement of the copper wire in the magnetic field produces electricity, which is then transferred through submerged cables to the mainland. The overtopper mechanism is one of the simplest wave power stations available. The mechanism is similar to a hydroelectric facility. The overtopper is anchored in open water, where waves fill several reservoirs that are raised above sea level. Water in the reservoirs is then released through a turbine, which powers a generator. The generator produces electricity, which then travels through a submerged cable to an underwater junction, where it is linked to a transmission cable that leads to a power station on shore. The newest and least used method of generating power from waves is the Oyster wave power mechanism. The Oyster technology captures the energy from waves and converts it to electricity, much like other wave power facilities. The Oyster is placed about 1 kilometer from shore and is positioned parallel to the shore. As the waves go over the Oyster pitches back and forth, which drives 2 hydraulic pistons. Pistons capture seawater and push high-pressured water into a power station on shore, where the water turns as a turbine and powers a generator. Wave energy is currently one of the most expensive forms of energy in the world, at around 10 euro cents or 14 cents per kilowatt hour. This is because the cost of the initial construction of the power facilities and the cost of maintaining power facilities in intense wave conditions is substantial. However, if enough facilities are constructed and technology improves, the cost of wave energy could drop substantially. Also, the only fuel necessary for wave power is seawater, which, with enough investment, could prove far more economical than fossil fuels. Wave power is primarily available on the western shores of continents, such as the Pacific coasts of North and South America. Today, the OWC is the most common wave power technology, and is one of the oldest wave power technologies. Invented to power beacon buoys, the floating OWC were tested between 1978 and 1986 by Japanese scientists. From 1985 to 1988, the Tofte Power Company in Norway tested a land-based OWC, though it could only produce 0.5 kilowatts. The plant was closed, but in 2000, the power company opened an OWC on the Isle of Islay, which produced 250 kilowatts. The company that runs the Isle of Islay plant, named WaveGen, also built a similar plant on the Azores Islands. The German power company, Voith Siemens Hydro, has built a small plant in Motrico, Spain, and plans on building a 3.6 megawatt, 36 turbine plant in Lewis, Scotland. Plants exist in Trivandrum, India, Sakata, Japan, and Dawashan Island, China. A project is underway in Reedsport, Oregon that would use the Archimedes wave swing technology. Wave power offers a renewable, clean source of energy available in some of the most populated areas on Earth. The potential for energy production from waves is enormous and reliable, and provides yet another energy alternative for the modern world. However, building wave power facilities is quite expensive. The technology still requires improvement to be adopted on a larger scale. Also, there's the possibility of negative effects on the flow of silt along coastlines, which could harm fish populations. The plant may also take up valuable waterfront space in heavily populated areas and could lower property values due to their appearance. In considering the negatives of wave power, the fact that waves may sometimes be too weak to produce energy must be considered, as well as the fact that waves are immensely powerful and can easily damage expensive facilities. However, the negatives of wave power are much more hypothetical than the positives. The large wave power infrastructure offers a simple, clean, and eventually cheap source of renewable energy that could contribute heavily to the energy consumption of our nation and our planet.